Recording.
It's a pleasure to present Louis Tebou from Florida International University. Louis is an expert in asymptotic behavior of PDE and controllability of them. He did his PhD at Met University and has the habilitation from Strasbourg University. So please, Louis, you can start now.
Okay. I want to thank Professor Luz de Teresa, a good friend of mine, who has invited me to speak at this international seminar. I also want to thank the organizers of the seminar for accepting the invitation, and thank you very much. And so we'll be talking about interacting flexible structures with localized strong damping mechanism. So we'll discuss semigroup regularity and stability. So I'm going to I did this work with some collaborators. So the next step will be to list those. So with Irena Lashechka of University of Memphis, we discussed regularity issues for plates, Euler-Bernoulli types of plate equation. First, we discussed the case where the damping is localized and is structural. That means type of square root damping. And then we also discussed the second work. We also discussed the case of localized Kelvin-Vogt damping, regularity issue and stability. And then with Kais Amari, Fatih Yassin, Suleiman Kadri Aruna, we discussed interacting membranes. So you have basically two wave equations. The damping involves the sums of the gradient of the derivative. That means basically a Kelvin-Vogt type, but localized, right? And singular in the fact that the matrix that defines the damping is singular. So we discussed stability issue for that system. So now I'm going to give you an overview. I'll give a brief history on regularity issues for abstract differential equations. Then I will discuss the case of Euler-Bernoulli plate with localized structural damping. Then we'll, of course, the model formulation, regularity, exponential decay. And then we'll move to Euler-Bernoulli plate with localized Kelvin-Vogt damping. Again, model formulation, Gevrey regularity, and exponential stability. And polynomial here also, if we remove any smoothness assumption on the damping, then we have just polynomial stability. Then we discuss the case of coupled wave equation with localized singular Kelvin-Vogt damping. So without, again, model formulation, polynomial stability 1, polynomial stability 2. We also discussed logarithmic stability, but I don't think we'll have time to go over that. Then I will share some final comments and open problems. So what I'll be talking about, what motivated this work was the initial started back in the beginning of the 80s with Russell and Chen, who considered this abstract differential equation. And the interest was to determine under which condition on the damping, this B operator is what we call the damping operator, right? What will be the relation between B and A so that the associated semigroup is analytic? Why are they interested in analytic semigroup? Because this has a big importance in control design, right? When you have a semigroup that is analytic, that means basically the high frequency dissipate very fast. And so you can view a system like that, like a finite dimensional system. And for engineers, this is very important. So damping is one of the most important. Any physical structure generates damping. Okay, conservative system, we have conservative system in math, but in the nature, we cannot find conservative system because you always have some damping involved. Viscous or frictional are exterior to the material, but Kelvin-Vogt damping type originates from the material itself. So you have what we call viscoelastic material. But they prove that the semigroup associated to that system is analytic, therefore exponentially stable when B is proportional to A1/2, that's the case of structural damping, or A, that is Kelvin-Vogt damping. Then they raise the following two conjectures. The semigroup is analytic. There exists constant ρ1 and ρ2 positive such that we have those two inequalities. The second one, that exists constant ρ1 and ρ2 positive such that we have, again, those two inequalities. Okay, why are such classes of damping operator important? Yeah, as I said, from a modeling perspective, structural or Kelvin-Vogt correspond to viscoelastic material. For such damping mechanism, the high frequency mode of the dynamical system are damped out as much higher rates than the low frequency modes. Therefore, such dynamical systems have behavior akin to those of finite dimensional system, and as a consequence are more preferred from an engineering perspective. So partial solution to the conjecture. So in one of the result of the work, Chen and Russell, they prove the following. So they almost responded to the first conjecture, but the problem is that you see the parameter on the left and the parameter on the right are related. Okay, so it's not exactly what they wanted. So in the same paper, they also provided a partial answer to the second conjecture, provided extra conditions that are difficult to check were imposed. Then afterwards, so we had to wait 7 years, right? In 1989, Shupin and Roberto Trigiani, under the conditions, they were able to answer not only what they raised, but even better. So instead of A1/2, you have from an exponent alpha between 1/2 and 1. And still they proved that the semigroup is analytic. So that answer more than what was expected from the first conjecture. And then analytic, in the same paper, they proved that the semigroup fails to be analytic when alpha is strictly between 0 and 1/2, but it's differentiable. So we see that later they will prove more. In 1990, they investigated further the case where the exponent is strictly between 0 and 1/2 and showed that the semigroup is actually of Gevrey class S for S greater than 1/2. Gevrey class is something that is between analytic and infinitely differentiable. Now, example of application. So you have the plate equation with structural damping. So this structural damping, so we know that the semigroup is analytic in this case. Kelvin-Vogt damping, again, in this case too, the semigroup is analytic. You also have the wave equation with Kelvin-Vogt damping. The semigroup is also analytic. Now, if you look, those work involve the case where the damping is globally distributed in the domain under considerations. Now, from a practical point of view, it would be better to have the damping localized. Why? Because advances in material science has led engineers to bond parties of viscoelastic material to an elastic material in an effort to suppress vibrations. Thus, from a practical point of view, it makes sense to consider localized damping mechanism. Now, the problem with localized damping mechanism is that you have your damping localized in a region, and then you want the effect of the damping to be generalized to the whole domain under consideration. Okay, in the case of frictional damping, linear or non-linear, you have a body of work, right? Whether you are dealing with wave equation or plate equation, you have a much better understanding for frictional damping. We have a lot of work that discuss the stability of the semigroup or stability of energy decay, etc. If the damping region for the wave equation, we know that if the damping region is arbitrarily small, then we cannot expect a decay rate that is better than logarithmic. If the damping region is large enough, we may expect exponential decay of the energy. We have to have intermediate situation where polynomial decay occurs, right? Even in the case of linear damping. Because if your damping vanish, right? Or if you are in a rectangular region and the damping is only in one part of the region and the other, you separate into two regions, the damping in one part, the damping in the no damping in the other part, then the geometric condition will fail. That means your damping region is not big enough, but you still have polynomial decay in that case. And now, when it comes to strong damping, right, especially localized Kelvin-Vogt damping, and the focus has been in the literature on the wave equation, right, and only stability issues. So we know a lot of things about the wave equation with localized Kelvin-Vogt damping, right? But for plate equation, we don't know much, right? So here, due to high order of the damping, exponential decay fails, even when the damping region is large enough, unless you require that the damping coefficient is not only smooth, but also satisfies a structural condition. So when the damping coefficient is only bounded measurable, only polynomial decay is expected, even if your damping region is large enough, okay? And logarithmic decay if your damping region is arbitrarily small. Now, when it comes to regularity result, there's very scarce and limited to one-dimensional system. So in the one dimension, what we know, transmission between an undamped wave equation and a wave equation with Kelvin-Vogt damping exhibit an eventually differentiable semigroup, provided the damping coefficient is smooth enough and vanishes at the connecting point at an order greater than 1. The transmission between an undamped Euler-Bernoulli beam and an Euler-Bernoulli beam with Kelvin-Vogt damping exhibits a semigroup of Gevrey class. This one is really very recent, very recent. It was in 2021, I think. Gevrey class. This is, again, one-dimensional. No regularity result was known in the multidimensional setting. So this is what prompted us to look at our first problem, right? So you have Euler-Bernoulli plate with localized structural damping. This is structural damping, right? So the D here, which is the damping coefficient, is allowed to vanish outside of the little omega. So you may view this as you have an elastic material where D is 0, right? And then you have a viscoelastic material where D is positive. And it's the interaction between those two that we want to study, the semigroup. How is the semigroup of such a material? Okay, let me go back. It is known that you have an analytic semigroup when little omega is big omega. Now let's introduce our functional setting. So we're going to transform this into an abstract differential equation, but for that we introduce the corresponding energy space, right? Define the operator and the domain of the operator when D is smooth enough will give us H4 times H2 0. So we have all the regularity we need. And so we can transform our system, right, into this abstract differential equation. And one can show that the dissipation law, right? The operator A generates a strongly continuous semigroup of contraction. The semigroup is strongly stable, right? So those are things that are not difficult to prove. So our first result. So here I'm going to present in the case where the damping region is just a color around the boundary of big omega. But the result was actually proved in the more general situation where the damping region is type piecewise multipliers of Liu or Martinez. All right, so not only we need the damping region to be big enough, in our case here in this presentation, a color around the boundary. So the damping coefficient must be smooth, right? And also satisfy these structural conditions. So on the gradient and then the Hessian must satisfy those estimates. If we have all those, then and the damping is coercive in a smaller region, control region, then the semigroup is of Gevrey class S for every S greater than 5/2. Therefore, the semigroup is infinitely differentiable. Okay. Consequences of Gevrey, the semigroup is instantaneously differentiable, in particular, infinitely differentiable, instantaneous regularity. The semigroup is exponentially stable, so you have instantaneous regularity, and then the semigroup is strongly stable, then exponential decay will follow. The semigroup satisfies the spectrum determined growth property. So this gives us the best rate of decay, of exponential decay. Now, the main idea of the proof of our Gevrey class regularity is based on Taylor's thesis, right? A sufficient result that he gave there, which reduces our search for Gevrey regularity to estimating the resolvent along the imaginary axis. So all we need to do is to prove that the resolvent along the imaginary axis is big O, right, of absolute value, lambda, minus 2/5 as absolute value lambda goes to infinity. So that means for lambda large. To achieve this, so what do we do? First, we work in the region where we have the damping, right? So localized kinetic and potential energy. That's the first thing we do. Second, we use geometric propagation of regularity. So here we are going to use the equation, right, and a first order multiplier to try to propagate the effect of regularity from the control region, right, to where we have no damping at all, damped region to undamped region, to everywhere in the set. Then, along the way, we are going to have to show where we lose regularity. And then at the end, we'll compute the loss of regularity and then complete the proof. All right. So if we pick U in H, we know that we have Z in the domain such that we have R lambda. Z minus AU, Z is U. Okay. Now, using velocity decomposition, damping, structural condition, interpolation inequality, we are able to prove that the localized kinetic energy satisfies this estimate, an estimate like this. I will not go into details. We don't have time for that. And using the multiplier D, V bar, then we are able to estimate also the localized potential energy. Now that we have these, we can estimate the localized energy, right? Get this estimate. And then our first estimate, when we use an appropriate first order multiplier, we can derive this estimate. So we see we want to estimate Z in terms of U. So you see already here, we have a loss of regularity already because you see we have B minus 1/2. To have analyticity, we should have B minus 1 instead of B minus 1/2. So we are already at minus 1/2 already. Okay, so, and then you see the localized potential, localized kinetic energy, right? So when you do this estimate, you get those terms, and that's why we started by estimating those guys. Okay, you also have the localized Hessian. This is also a big guy that will, again, further produce a loss of regularity. All right, so you can estimate the localization in terms of the localized potential energy, like this. And then we report. So you see already the red term, we go from minus 1/2, now we have minus 2/5. Meaning that this term, we can estimate it like this. This is the worst we have gotten so far in our estimate. And then now when we collect, finally we collect and we derive the estimate that we wanted. That means norm Z, this. This proves that, remember, Z is resolvent operator applied to U, right? This proves that the norm of the resolvent operator is less than a constant absolute value of B minus 2/5. That's exactly what we wanted. So now with this, we have completed our discussion on Euler-Bernoulli with localized structural damping. We move to Kelvin-Vogt damping. So one may argue, why do we need to study these two differently? First, we know that when the damping is globally distributed, whether structural or Kelvin-Vogt, the semigroup is analytic, okay, in both cases. But now when we localize, what happens is that in the case of structural damping, you still have an operator that exhibits a compact resolver. But in the case of Kelvin-Vogt damping, your operator no longer has a compact resolver. In the case of localized damping, localized structural, we start with basically nothing because the localized structural damping give us the dissipative property, give us, right, an estimate on the gradient of the velocity, which is localized. All right, we don't have an estimate of the gradient of the velocity localized itself, so we have to do that. Here we start with Kelvin-Vogt. We have an advantage because the localized estimate given to us by the dissipation law involves the Laplacian of the velocity. And so with this, we get exactly the localized potential energy for free, basically, okay? And so now we are going to turn around and try to use that knowledge to get an estimate of the localized kinetic energy. Okay. So the operator A is now given by this. And here we don't have the type of regularity we had before, right? Because the V here, little v here is just H20. So even if your D is smooth, as we are going to assume in order to prove our regularity result, you see that the term involving delta, the Laplacian of D Laplacian V, that term will be H minus 2 only, okay? The best we can have. So your U is not more regular than H20. That's a problem already. So we can reformulate as before, right? So we have the dissipation law now given by this. Again, here too, we can show that the semigroup is strongly stable. So we have this. And so the result here, again, the hypothesis on the damping region is the same as before. And the constraint, exactly the same as before. And so the semigroup here in this case is S greater than Gevrey plus 7/2. Okay, S greater than 7/2 because we have this resolvent estimate. So the semigroup is infinitely differentiable. So the idea of the proof is the same, okay? Taylor sufficient condition. But to achieve this, first we need good estimate on localized potential and kinetic energies. Geometric propagation. So it's basically the same steps, but we'll see there are some differences. Compute the loss of regularity, complete the proof. All right, so we start with the dissipation law already give us this estimate on the potential energy. This is nice, right? Because this is exactly what you will get also in when the damping is distributed everywhere. If D is 1, then you get exactly the same thing. So we don't lose, we haven't lost anything here in terms of regularity. Now let's move to localized kinetic energy. So you just multiply your equation by this, and then you get this estimate. So again, if you look at this term here is the localized energy. If D is 1, this is exactly what will lead us to get that the semigroup is analytic. So there is no loss of regularity here when we estimate the localized energy. If we compare this to what we had before in the case of structural damping, the loss was already big when we were evaluating the localized energy. Now, after this, we have to estimate the total energy. So first order. So now you see here at this point, we have lost already 1/4. Let me see. Oh, more than that. Because it should be B minus 2 here. Now we are at B minus 3/4 at this stage. All right. Now, so you have the bad term appears in red. Now we have to estimate that term. All right. Estimating it leads us to this. So you have the term with U here, and then a B minus 1/2. Those are the terms that are going to lead to loss of regularity. Now, if you estimate this term here corresponds to what we had with the Hessian, the localized Hessian in the case of structural damping. So this is a term that will make us lose a lot in terms of regularity. So we go from minus 3/8 to minus 2/7. Okay, and then this is the ultimate estimate that will give us the desired estimate leading to the claimed semigroup regularity. Now, if we remove all smoothness assumption on the damping coefficient, right? Then all we know about the semigroup is that it is polynomially stable. So we have this estimate of the semigroup. That means the energy decays like big O of t minus 2 as t goes to infinity. Okay, so to do that again, we use the frequency domain approach, estimating the resolvent along the imaginary axis, right? So all we need to do now is to prove that the norm of the resolvent is big O of absolute value of lambda. Thanks to Borichev and Tomilov, we can then deduce the polynomial decay announced. To achieve this, we no longer have smoothness, right? Somewhat we have to proceed differently. Again, we have to propagate the effect of damping. The remaining terms involve and localized kinetic, estimate the term involving the function, estimate the localized kinetic, and then conclude. All right, so basically when we use the first order multiplier, we get to this point, right? Those are the two terms to be estimated, the localized kinetic, and then this term that we had before, but we no longer have smoothness of the damping coefficients. Okay, so I just work on this term, right? The term with big U and big Z to simplify things. And then we estimate this term using a duality argument. And finally, using resolvent equation, we get this, the estimate of the norm of the velocity in -1. Then we combine, we get this estimate. So you see that this b minus 1/2 and this will give us what we need. Finally, we estimate the localized velocity, kinetic energy. We get that. Gathering those estimates, we get what we want. Okay, so we get this, and then we apply Tomilov and Borichev, and we derive the claim polynomial decay. Now, in the case of the wave equation, so we consider this system. So you have here, the damping mechanism is singular because the matrix defining the damping is singular. All right, so we must assume that the speed of propagation in the U and the speed of propagation in the W are distinct. Otherwise, what happens is that the system will be unstable. You just take U plus W, that one will be damped. And if you take U minus W, when C equals D, you take U plus W, it will be damped exactly as there. And U minus W will be undamped, will be conservative. And so the system will always oscillate all the time, okay, if C equals D. So we have to assume C, not D. That's the first thing to note. Again, the damping, you see the damping is the type Kelvin-Vogt and involve the sum of velocity. So this falls in the framework of simultaneous stabilization. So we have the same damping mechanism, right, in the two equations, and you want to simultaneously stabilize the system. So that was introduced, I think, by Russell, right? And the first one involved exact controllability, the Maxwell equation. And then Lyons, in his book on controllability, extended the controllability result to wave equation to also a system of plate equation, etc. And Harrow studied the case where the control is inside the domain and mostly on the wave equation. So here we are interested in localized Kelvin-Vogt damping. What happens, right? Now, we note that if the damping is distributed everywhere, even in this situation, what we know is that the semigroup is not differentiable, okay? Unlike the case of a single wave equation with Kelvin-Vogt damping, globally distributed Kelvin-Vogt damping, right? The semigroup is analytic. Now, when you localize, you lose that property. In 1D, almost provided your damping coefficient vanishes at a certain order, right? And here, we are going to formalize, again, as before, the functional framework now is given by this energy space and the corresponding norm. Then the operator, we define the operator A as sure this A as well as does not have a compact resolvent, so makes things a little bit tricky. We write, we get into the abstract formulation of our problem. So we have the dissipation law. We can show that the operator generates a strongly continuous semigroup of contractions. The semigroup is strongly stable, right? No problem there. Now, our first result. Okay, so again, omega, the damping region is as before, and we have those sets, omega 0 and omega 1. Right? So the damping coefficient must be C2, right? And must satisfy two structural conditions. Okay, I can comment on this when we have a single wave equation, right? When we have a single wave equation with localized Kelvin-Vogt damping, what we need is just the gradient. All we need, the damping coefficient must be C1, and the gradient must satisfy that inequality, but we don't need any condition on the Laplacian, and also the coercivity condition. And then the semigroup in that case is exponentially stable. But see what we get here. In this case of coupled system, what do we get? We get that the semigroup is just polynomially stable. Okay, so we get this estimate. And we were able in one dimension to show, using numerical computations, to show that we cannot expect exponential decay, okay, at least in one dimension. And seeing in one dimension, we cannot expect exponential decay. I doubt that in higher dimension we can expect, even if your A is much more regular. So the idea of the proof is the same as the one that we did before. So we rely on Borychev, Tomilov, and then we have to estimate the resolvent along the imaginary axis. So maybe before I go on, some of you might have questions, I don't know. Any questions? All right, so I will go on. So the idea is to prove that with U and Z given by that equation, right, the resolvent equation, norm Z is less than or equal to K0, modulus of lambda, norm of U. So I've given just the methodology here. Due to the fact that the damping is localized, we need first order flow multiplier to propagate the effect of damping. It's always the case. If your damping is localized, you need a flow multiplier to propagate the effect of damping. Okay, the damping. Yeah, here, the problem we have is that the damping is unbounded. The operator A does not have a compact resolvent, so solutions are not smooth enough to apply the first order multiplier directly to either PDEs. So we shall introduce new variables that have the requisite smoothness. Third problem, the matrix defining the damping is singular, making it tricky to combine the estimates. So first you get estimate on the UV system, on the WZ, and then you have to combine the two estimate, those estimate to get the estimate on the corpus system. This is why we need the speed of propagation of the two waves to be distinct. So the rest of the proof will go along the following steps. So smoothing of solutions. So we have to introduce new variables, right? That will enable us to propagate the localized effect of damping to the whole domain. Preliminary estimate. So we need to estimate, as in the case of Kelvin-Vogt that we discussed before, we needed to estimate norm V minus 1, norm Z minus 1. Same thing here. And appropriate flow multiplier to propagate the effect of damping. Third, estimate the localized energy. So we did that before. Here too, we have to do it. Since the dispersing involves the sum, but there is a little bit, here it is a little bit more tricky because you have the dissipation law involve the sum of velocities. So the idea is to express the localized kinetic using the sum of velocities, because that's what we know, okay? Then rely on the local equipartition of energy to estimate the localized potential energy. Then step 4, final estimate completion of the proof. So the main idea. Now, let's get into the smoothing. So we introduce this new function, phi, that satisfies this equation. So you see this look like the damping that we had, right? And so the dissipation law immediately gave us this estimate on that function phi, and then we introduce new variable u1 and w1. Remember, u and w are just h1. They are not more than that, right? And so the u1 and w1, they satisfy these two equations. And elliptic regularity show that both of them are h2, so you can apply a first order multiplier, right, on either on u1, on the equation with u1, the equation with w1, no problem, because you have h2 regularity. So first we estimate this norm, get that. Using appropriate first order multiplier, we get this. So we have localized kinetic, localized potential, energy, and then again, that term, that extra term. Then we estimate localized kinetic energy, we get that. Localized potential energy, we get this. And after that, we regroup and we get to this point. Now, so up to this point, if this term did not exist, exponential decay will hold, right? Because there is no factor of lambda in the term on the first line, okay? But this term here with lambda frequency variable, when we estimate it, that's where we lose the exponential decay property. And then just end up with polynomial. Now, the second result that we got, we say, okay, when D is smooth, C2 satisfy those constraints, we have polynomial decay. What happens if D is just bounded measurable? Right? If it's just bounded measurable, then the decay is worse. It's cut in half. The decay rate is cut in half, basically. So you go from 1 to 1/2. So the idea of the proof is the same. So I will not go into the proof of this. And then I will discuss just some further comments and open problems. So the two regularity results are valid for more general feedback region. So that's what I said before, that the region where we have our feedback control may be taken to satisfy the Liu piecewise multiplier condition, right? So your domain is divided in many subregions, and then you have the control in a very small region compared to what we have now, the whole equalar on the whole boundary. However, in the case of Kelvin-Vogt damping, the same constraint on D as in the structural damping leads to a Gevrey class. So we lose in terms of Gevrey if we take a more general control region, we go from 7/2 to 4. We were able to get the same class in Theorem 2 for a more general damping region. That means we could get the same result as in Theorem 2, more general control region. Now we have to introduce a new variable instead of the one that we used before, combined with commutators requiring the damping, a smoother damping, and one extra constraint to get the same class, 7/2. And the polynomial decay estimate holds for more general damping region as well, okay? Even in the case of coupled wave equation, logarithmic decay holds when the damping region is an arbitrarily small non-empty subset. Okay, let me see. Something happened here. I don't see. Okay. Regularity issue for both model under other boundary conditions, particularly the more interesting case of free boundary condition remain open, except for the case where the damping region is a collar around the whole boundary. You have a collar around the whole boundary, then you can use a multiplier that is invisible to the boundary conditions. So then you get the same result as before. But the more general control region, that's open. Optimality of the Gevrey regularity and rational stability results are also open. All right. Thank you very much for your attention. I'm done.
Thank you very much, Louis. We are opening the microphones if somebody wants to make a question or comment. Also, you can ask in the chat. Yes, the audio and the video are open if you want to ask somebody for our speaker. Very nice talk, Louis. I have maybe comments or questions. So this regularity that you get in A is like not useful for applications, no? I suppose that you cannot put like a patching with this regularity. Or yes, do you know something about that?
The regularity?
Yes, of A. So you say that A, in some cases, this needs to be T2 of omega, no? But I don't know if this is something reasonable for application. So really for application.
Really for application. Yeah, as for application, I say that generally what engineers, they do, they have an elastic material and they bond that with a viscoelastic material in order to try to suppress noise, right? So they use elastic material and attached viscoelastic. Now, when you attach viscoelastic, what we are learning here is that your viscoelastic should not be too far from the elastic material that you are using.
Okay.
Yeah.
Thank you.
That's how I understand it. The continuity of material, not too far. Yeah.
And also, as you know, for the single wave equation, there are results where they prove Pasua, and I don't remember which two. They prove that there is some overdamping. So if you put instead of only outdamping the derivative with respect to time, you put also a term in the position, let's say, you get better results in terms of exponential stability. Okay, so we can choose the exponential decay. If you put some term in the velocity and some term in the position. Have you tried to do something like that in your problems that maybe you can get a better result, not polynomial or something like that?
No.
No?
No. So you are talking about the case of non-autonomous damping, right? Where the damping is a function of time multiplied by what we have here.
No, not a function of time. So no, the result I am telling to you, I cannot write. You have like a local, so you can
Local damping, right?
Local damping.
Is it linear or non-linear?
Linear.
And the damping coefficient depend on x and chi, right?
No, because you are only putting a localized damping in omega, a characteristic function. If you put as only a term u sub t, they prove that you have an overdamping. So you cannot choose the exponential decay as big as you want. If you modify the constant in front of this damping, putting it bigger and bigger, larger and larger, you're not getting a better exponential stability. So
yeah, because at some point overdamping will occur, right?
Yes.
Yeah.
Some overdamping, so you cannot reach a better exponential decay. So what you can do is to add also a local term, but u, just in the position.
Okay, I see. Yeah, to try to control that.
To compensate with appropriate constants, at least in the one-dimensional setting, put b times u characteristic of omega in such a way that you can put you can obtain your exponential decay as big as you want. Okay?
Yeah, I see.
So I am thinking or wondering if you add another term here, for example, in your Kelvin void damping, you can add another term that depends on you.
That can give us exponential decay?
No, maybe you can get exponential decay or a better decay, polynomial decay. So
I see.
adding another damping, for example, adding the divergence A of x gradient of u plus w, maybe that's something. I don't know.
Yeah, I understand. Yeah, yeah.
Because sometimes this gets a better, at least for exponential decay, it works. I don't know.
So you were talking, the authors of that paper who are they? The paper you are referring to?
I can send you the reference.
Oh, okay. Thank you. Thank you.
In this moment, I don't remember it was well with. Maybe Hansen. I don't know. I can send to you.
Okay. All right.
Are there any other questions or comments? I don't see anything in the chat. Well, if not, thank you again, our speaker.
Thank you very much.